So, how do we estimate the right size of a residential battery energy storage system? In terms of photovoltaic size, things are a bit easier, right? And the recommendation there is usually to build systems as large as they can fit on the roof. But in terms of home storage, there are many factors to be considered. First and foremost are the user's goals. So, when deciding on a residential battery energy storage system, homeowners are usually motivated by two factors, and these are self consumption and self sufficiency. The first one is about maximizing use of of self-generated solar power with a view to putting downward pressure on electricity bills. The other one has to do with energy independence, a term we tend to hear more often since the start of war in Ukraine, and the ability for a household to manage off the power grid in an emergency. In both cases, however, there is no one-size-fits-all approach. And this gives us more than enough reason to deep dive into residential battery energy storage system use cases and best practices for sizing in conversation with experts from our initiative partner in today's webinar, GoodWe USA. Hello and welcome. My name is Maria Maish, editor at PV Magazine Global, and it is my pleasure to be your host in this webinar on this lovely Berlin evening. So without further ado, our webinar is tightly packed with topics, useful information, and insights, and this is what you can expect. First, we'll get an overview of residential energy storage system technology and terminology. Then we will discuss why lithium-based high-voltage batteries. Further topics will include backup power and self-consumption options, and this will be complemented by use cases, including best practices for system sizing. And finally, we will have our Q&A section that will be a chance for you in the audience to take part in the discussion. Now, representing GoodWe USA and joining us today, I'm delighted to introduce Jock Patterson, Technical Sales, and Michael Mendick, Country Manager, US and Canada. Jock, Michael, if you could briefly turn your cameras on to let the audience put faces to those names. Thank you both. It's a pleasure to have you here. But first, before we get started, a little bit of housekeeping and practical information about today's event for some of you who might be joining us for the first time. Please get involved and use your chance to tap on Michael and Jock's expertise and holistic business understanding today. So don't hold back, send any questions you might have via the Q&A tab, and we'll endeavor to get to as many of them as possible. One question that we often hear from you is, will the slides be available afterwards? And the answer is yes. All registrants for today's webinar will be receiving an email from the Big Marker webinar portal with a link to the recording, which can even be shared with your friends and colleagues after our event today. And of course, the PV Magazine webinar team is standing by to answer any questions you might have about the platform or any other administrative matter. So without further ado, I'll hand over to Michael, who will kick off the presentation by sharing some relevant information about GoodWe and the US energy storage market, and then pass the floor over to Jock for further insights. Take it away, Michael.
Okay, well, thank you for the introduction. And welcome, everyone. Really happy to be here. Since we started in the US market last year, we have had many questions from installers about sizing storage and storage systems. And this is why we are here to share with you some ideas and also get your feedback. My name is Michael Mendick, and I'm the country manager for GoodWe North America. I'm very glad to be at this seminar with you. GoodWe's vision is to be at the edge of innovation and provide solutions for solar and storage. We have sold over 3 million units worldwide. The company was started in 2010 and has been on the stock market since 2020. We have 8 subsidiaries globally, and the US is one of the youngest organizations. As an international team, we work very closely together and want to grow our global partnerships. Our production and R&D are located in the high-tech centers in Suzhou, and GoodWe is one of the top 10 inverter manufacturers, and we have achieved the double-digit market share in several countries. So since the start of the company in 2010, over 35 gigawatts have been installed, mostly in residential and commercial space. That's our area. And we have been voted as one of the top 3 energy storage suppliers globally. And I would like to share with you some of the market data that explain why we are so excited about this opportunity. We all heard about the news of ITC extension. It's great. And this is the projection by Wood Mackenzie that shows a continuous growth for residential PV year over year, every year. Maybe more exciting is to see how the residential storage is projected to grow to 5.7 gigawatt hours in 2026. That's soon. And that's a lot of batteries, you can imagine. This may correspond to 500,000 10 kilowatt hour batteries at some point per year. So now how you combine PV and storage together, Jock Patterson will explain. Well, thank you, everyone. Jock, it's on you. Thank you.
Thank you, Michael. And I'm happy to be here too. And thank you, PV Magazine, for the opportunity. We have a lot of material to cover, so I'll be going rather quickly, but remember, you can see this material again by getting the slides or looking at a rebroadcast of this video. Today's scope is ESS, or Energy Storage Systems for Residential Use. The ESS abbreviation really stands for Grid Interactive PV Battery Energy Storage Standby Power Systems, right? That's a mouthful, but we're saying that we're talking about residential systems that are tied to the grid, are split phase, and the only on-site generated power is from PV. With these systems, we can provide standby power. We'll define what that means. And this will be power used for either partial backup or full house backup. There will be some other ESS applications we can talk about, but our focus will be on backing up power when the grid is lost. We can look at existing PV systems and adding battery to them, or completely new installations. And this is referenced by DC and AC coupling, which we'll describe. There are a lot of batteries out there, and we can't talk about every chemistry, but we will focus on a common one, that's lithium ion, and to introduce, for those who aren't familiar, high voltage and the benefits of a high voltage battery. We will touch on the fact that generators are used, but in our simulations here, they will be secondary power systems to the ESS, should the ESS go down. Our subjects are as follows. We're going to talk about basic terminology, so we're all on the same page. A little mention of the NEC, always good in any webinar in the US. What our equipment consists of for an ESS, the different topologies you can see, for example, DC-AC coupling, partial and full backup, how to determine the load profile of a consumer, a household, and with that information, then determining the proper sizing of an ESS. So let's begin. With terminology, there are a lot of words that are going to be familiar. I just want to make sure we're all on the same page. For DC and AC coupling, imagine two PV arrays, exactly the same, but one, the one on the left, connected to a PV inverter. That's just a grid-tied inverter. However, the one on the right is a PV hybrid grid interactive inverter. They both receive the same power from the PV array, but if you want to add a battery to this system, you end up having to get a second inverter for the system on the left, a battery inverter. And the battery inverter brings that power into the battery that originally came from the PV array. So the PV array to battery connection is through an AC circuit on the left, and on the right, it's through the DC bus inside the PV hybrid inverter. So that's DC and AC coupling. A note that microinverters can only AC couple because they are PV inverters. In any backup scenario, we can describe at a high level whether it's using AC or DC coupling and whether it's partial or full. And we'll be looking at combinations of these things. Other terminology to be familiar with is AC coupling is often referred to as retrofit because it applies in the case where we retrofit an existing PV system by adding battery. And a DC coupling is a new install, just doing a PV hybrid inverter with storage. Partial backup is often referred to as essential loads, and you need to add a backup panel, where full backup is all loads, where you need to provide a disconnect method from the grid. The NEC refers to backup power at the residential level as optional standby power. Optional as in it's not legally required, and standby meaning it's not continuous. So you're not off grid here, and you're also not doing PV generation from your neighbor's house, dragging wires over to your property to power your batteries. You guys are not in the power business. This is all about what you generate on your site for just your loads. Distinction that's important is these systems are standby power systems, not uninterruptible power supplies, meaning that we can't guarantee there isn't a significant latency to the transfer time from a loss of grid to the backup system. We'll be talking more about that. So we have essential loads, which are those few circuits that the homeowner would really like to be backed up. And that's a simpler solution generally, right? Sometimes it can be difficult to do essential load wiring, but generally it's a simpler solution. And if you're doing essential loads, it's important to choose the right ESS for it. For full home backup, this doesn't mean running all loads in the home simultaneously. Like we have to explain to the customer, the full house backup means that all loads have the potential to receive backup power, but some load management might be required because you do not want the case where your total load exceeds the output of the ESS system, or that system will shut down. A word on the word essential. These are loads that you would like to have run, but they're not considered critical loads by any authority. Critical load is defined differently by the NEC. And if you truly have a critical load, like an oxygen generating machine, those should be connected to a UPS, which in turn can receive further backup power by the SPS, that is the ESS that you provide your customer. In providing equipment to do the transfer and support the load from the grid to your backup system, this equipment must be able to handle and be rated for that kind of use and load. So in calculating your loads, be very mindful of ones that are reactive loads. These are loads that can use more power than you think, but they don't actually consume. They draw a lot of power, but they don't consume it all, so it can be misleading. You need to pay attention to those type of loads and highly variable resistive loads that have a high inrush current. Most will have a nameplate rating showing that, but we'll talk about how you can also just measure these devices for their demands, power demands. Whatever your solution, absolutely use a pure sine wave inverter. Now on to the equipment. For batteries, we're going to just focus on lithium-ion batteries because they're popular and they have a relatively flat discharge curve. They're high energy density. They can do many cycles, and they're relatively light, even though they are not light in a general sense. We are going to look at high voltage versions of these. Why? Because that's becoming more popular and people might not be as familiar with them. So instead of your regular 48 volt system, we're talking 100 to 400 volts. And instead of needing the big red 4-aught cable that you see here, you can use the smaller black building wire, maybe a number 6 gauge, simply because we're at higher voltage. So that saves you on copper costs and dealing with bulky cables. You can also run longer lengths. So your battery doesn't have to be next to your inverter. It can, for example, your battery might need to be in the garage for environmental reasons, right? It gets too cold outside or too hot, but your inverter can put up with that temperature swing. So you put your inverter outdoors and your battery indoors, and you do not have to deal with thick cables running through walls, just simple building wire. This presentation is about single family or duplex homes, not multi-family residential systems, but the code will tell you that you shouldn't be using these high voltage batteries for these single family homes. Well, they make an exception. If you are using an ESS that's in a cabinet, it's protected, there are no conductors or contact points that result in high voltage exposure, then you can use ESSs up to 600 volts. Examples of some lithium high voltage batteries, two here, the BYD HVL on the left is a lithium ferrous phosphate, and on the right is the LG Resu Prime. The lithium ferrous phosphate is becoming more popular, but the NMC has been popular because of its familiarity in electric vehicles and its greater energy density. However, let's compare two versions of these that are 16 kilowatt hours each. And we can see that in general, LFP designs provide more power than the NMC. However, that comes with greater weight. So the model, the BYD, shows it's floor standing. The LG can be on the floor, but also hung on a wall because it's generally lighter. So you have to find out what are the preferences and limitations at a site. You know, what does the customer prefer, and maybe the AHJ make tougher, right? If you want to hang that inverter on the wall, maybe that adds seismic difficulties. You have to get a wet signature from an engineer on that. So you have choices with lithium batteries. The inverters, the ESS inverters, are going to be a battery only if you're doing AC coupling to an existing PV system, or a hybrid, a PV hybrid. In both cases, you need to know whether that ESS inverter includes an auto transformer. Why is that necessary? Well, if you want to back up 120 volt circuits, you need to derive a neutral. That neutral is lost when you no longer have the grid. So you have to derive a neutral from the power that you're exporting from the, or output from the inverter. These inverters typically come in two designs. Either there's a single AC circuit leaving them, as represented by the solid blue line here to the main panel, or the dotted line represents two circuits where we have an on-grid circuit that goes away, opens up when the grid is lost, and then there's a backup circuit in its place. The two-circuit design is great for essential load panels, and the single circuit is better for full home backup, but you can use either one for both cases generally. If you are going to have an existing generator that needs to be useful in this system, we can generally find ways to set up a relay, or the inverter may even have a dry contact in it to indicate to the generator or its ATS when to turn on. We are installing potentially a lot of equipment here, so it's always nice to have embedded metering, embedded rapid shutdown transmitters in these ESS inverters to save space on the wall and just look cleaner. When we add our battery in this diagram, it does add to the complexity of looking at some of our topology diagrams. So what we're going to do here is just say, yes, we could physically have a separate inverter and battery, but we're going to represent them in our diagrams on the right, looking like they're one unit just for simplicity of the drawings. For example, commonly known Tesla Powerwall is a single cabinet, but it doesn't have to be that way. to the right of that is an Panasonic EverVolt, where you can actually separate the inverter from the batteries. So that's more of a preference. In the case of switching over when the grid goes down, you have to make sure you have some sort of automatic transfer switch. And if your inverter doesn't have that built in for essential loads, then you have to get an external one. If you're doing full backup, you're going to have to get an external one. And we'll look at diagrams showing that. The beauty of these high voltage systems, although the Tesla technically is a 50 volt, is that they're in a cabinet where none of the wiring is exposed. It's very clean. It can't be exposed, and it's nice that it isn't. Very clean install. Remember that for microinverter systems, you'll be doing AC coupling, and you'll have a little less efficiency because you have to go through the rectification process of converting AC back to DC. Now on to ESS topologies. There are many slides here, so I'll go through them quickly. Remember that you'll be able to view this stuff again at a future date for posterity, and if you miss anything this time through. So we're going to look at essential load solutions for new installs. What we have here is a ESS in the center, receiving power from an array that's connected to the main service panel. And we have an essential loads panel. The power from the grid can come into the main service panel and pass through on the on-grid circuit to the ESS inverter, where it then can be passed through further to the essential loads panel. So that's how power moves to the essential loads panel when you're on grid. When we go off grid, then it's only our PV and battery providing power to the essential loads panel. The switch to turn off the on-grid connection is embedded in this ESS. So I'm going to turn off my video just so I can see more things here, and get a crayon out for you if I can. 1 second. Got it. So that's what I'm saying here. The ATS is embedded, and it does the switching. You don't need an external device. In this next example, imagine there is a generator. Now the generator is connected to an ATS, but it is not connected to the backup circuit of the ESS. The ESS is your standby power source. So when the grid goes down, the ESS provides power to the essential loads panel, not the generator. However, if it's nighttime, like I'm simulating over here, then we have no PV to recharge the battery, and theoretically the battery could run out. Before it dies out, it can send a signal to the generator, ATS or generator, to take over, in which case the battery cuts out and the generator then takes over, and the ATS has done the switch to the essential loads panel. In a different design, we can have no ATS, right, as part of our ESS. It's not embedded, so you have to have something external. It's got a lot of different names. MID is really not the appropriate name for this location of the device, but you will see a lot of different names for these. So you'll have to make sure you get that external device. The beauty of having an ATS embedded is not only that you don't have to get an external device, but it generally is going to have a faster transfer time. So some of your loads won't have to restart on transfer to backup, because the embedded ATS switches so quickly that it can support the continuous operation of the essential loads. Now we're going to look at a retrofit of essential loads. Here, the PV inverter and array, well, the PV inverter, which was originally connected to the main service panel, is going to be relocated to the essential loads panel. Why are we doing this? Well, if the grid goes down, the PV inverter is going to shut down because there's no AC waveform anymore. So if we connect to the essential loads panel, we create our AC coupling and get our AC waveform from the battery inverter. And by the way, yes, this is a battery inverter. You don't need a PV inverter. We could do one, but a battery inverter, if you don't need additional PV, is all you need. So when the grid goes down, the ESS contributes power to the loads. The PV inverter contributes power. The PV inverter might make more power than is necessary. And so on a bidirectional ESS setup, that energy can flow back into the ESS and charge the battery. Now, when we have this kind of AC coupling going on, it's good to note, and you would like this to exist, that frequency watt functionality exists in the existing PV inverter. It may be an old inverter and not have it, even a slightly newer, but you should still test. And what we mean by this is if the PV inverter is overproducing in the sense that the essential loads don't need more power and the battery is fully charged, the way for an ESS to communicate to the PV inverter without additional wiring is to change the frequency of the AC waveform to tell the inverter to ramp down. That's our frequency watt functionality, and you want to make sure that exists in this type of setup. And we also have the same sort of setup, but we have the external ATS again, right? So that's another possibility. Now we get on to full loads, new installs. Here we have to have a way of disconnecting from the main service panel. So that's our external ATS between the main service panel and utility grid, or MID device. And we have to have communications to it because the ESS is in charge generally. So it actually is saying when to make these transfers. This, again, is still an example of the dual AC circuit where when the grid goes out, we lose the on-grid connection, but we still have our backup circuit. However, we could have a single AC circuit such that when the grid goes down, the so-called on-grid circuit stays alive. It becomes the backup circuit. And finally, for our views today, although there are more possibilities here, I've drawn something that absolutely cannot happen. If you had this set up, your customer is not getting any backup power. If the ATS is put in this location, when the grid goes down, no power is going to make it to the main service panel. So if you don't have an essential loads panel and you're just doing this, your customer gets no backup power. So, we could also do retrofits, right? We can do full loads in a retrofit scenario. So again, we have the PV inverter connected to a load panel, but this time it's a main service panel. That's where it's doing its AC coupling, not through an essential loads. And now we don't have to move the PV breaker out of the main service panel to another backup panel. And operates basically the same way. So let's get into what I consider the most important part of this presentation, load sizing. The load sizing is going to be based on what your customer wants and what they can afford and what the site permits physically and electrically. So there are a lot of things to consider. I've listed them here. Again, you can review them when you review the slides, but we're trying to look at power and capacity needs and meet customer expectations for sufficient backup, but being an affordable system. If the customer moves towards the desire of full home backup, they move towards what is generally a more expensive system. Now, it doesn't mean it can't be done, but load management becomes more important as you move to backing up more of the system. The load management topic is big, and that's a whole nother webinar, but that can be in the form of the homeowner taking on responsibility about not running too many loads, or you providing a load management solution, both hardware and or software based, that is out in the marketplace. Okay, so you're going to do this load assessment, load profile examination. And I'm going to tell you, before you do that, see if you can get them to replace the inefficient loads, right? This is the low-hanging fruit that they should do anyway, even before getting a PV system. So a simple example here is you've got represented by the blue area of this chart, the amount of energy consumed by 60-watt light bulbs, 10 of them, right? So that's 600 watts of power over time. And you could get the same brightness of light from using 10 LED lamps at 1/12 the energy consumption or power consumption. If you replace these, that allows you essentially to run backup longer, right? By just changing the lights, you have more backup time. When you've decided if you want to do partial or full, here's a flow chart to help you figure out just exactly what the load profile is if you're doing partial or full. I'll talk about each of these in subsequent slides, but know that when you come out with your load profile, you're coming out with either historic or current usage. You should also factor in what's on the right side of this, and that is, will you be adding a room to the house? Are kids going off to school? Are you getting rid of an old hot tub? Are you buying an EV? What's going to change significantly your load profile? And factor that in, because you want to get your customer an ESS for their future, not for their past. So the simplest method, if you're doing a full home backup, is just to look at bills from the past. You can either download those from the website. There's often something called a green button, gives you a lot of detail on energy usage, or you just pick up paper bills. The other way is, if you're getting a new house in which you don't have any history, you can look at something like the US's EIA site at this particular link and drill down to your geographic area to find typical consumption for houses of a given size. If it's a brand new house, the builder may have an estimate. They did some calculations when they built the house, what they expected it to consume. If you move from a home to a new home, maybe your energy profile is going to be very similar. So you could take the usage from your previous home and just extrapolate based on the change in the house size and efficiency of the house. And there's also the case where it's a new home to you, but someone else owned it before you, and you can get usage from the prior owners. So if I'm doing a full home evaluation of, and I don't want to look at the historic usage, I want to look at what's happening today, I'm going to do a metering of the site. So I'm going to look at the meter, the utility meter, and get a reading, and then I'm going to read it again 48 hours later, and divide that total usage by 2 to get your daily consumption. You can do it for a longer period too. You can do it for a whole week. The idea is to figure out what is your typical daily consumption. Now, if you're not going to back up all loads, but most of them, then you're having a large essential loads panel, or you just know you're not going to use some loads. You're going to immediately shed those loads on transfer on the full house backup. You can do a metering with certain circuits opened up, right? So you simulate for that 48-hour period a partial backup by opening certain circuits. Then you can take your end reading and subtract your beginning reading to get your utility usage. Now, if you have an existing PV system, that's going to mess up that reading. You have to factor that in. So if you have a unidirectional meter, you're going to have to add in your existing consumption to that. If you have a bidirectional meter, you're going to have to add in your existing production. That stuff, if you want more help on, I can help through contacting me, and my contact information is at the end of this presentation. If you're doing a meter metering of essential only loads, you can get down to the individual loads or load circuits and using devices like you see on the right here. This is, again, when you're doing bare bones backup, right? You only have a few circuits or loads. This is really useful for those reactive loads that are pretty hard to get a good gauge on their usage, either because they cycle a lot or they have this great inrush current that's hard to determine. You can look at consumption over time with devices like you see on the right. They may even be good at picking up the inrush current. However, I would have a quality clamp meter and set it to max and get the RMS value, the true RMS value, or know if it's a peak value from your Fluke device or whatever you're using. So you can get the inrush current by starting up that AC compressor and having your clamp meter over it. Understand that most of your resistive loads will not vary a lot, so just getting nameplate rating off them will help you. Although a lot of different types of loads that we call resistive are variable resistive. LED lights, even the old incandescent lights, when the filament is cold, that tungsten filament is highly conductive. But the moment it starts to heat up, it becomes highly resistive. So there's a great inrush of current initially. So there are a lot of inrush current devices. It's the ones that are high in nature that you care about. Don't worry about the lights. So now you've got your load profile, you can want to size systems. A simple way to do it well, it doesn't look simple here, but I'm not going to do all the circuits. We're just looking at an essential loads panel. So it's a few circuits. So it's easier to do by hand, or in this case, a spreadsheet. And each of the lines here represents a different load, but the gold rectangles represent what circuit they're on. So there are really 3 circuits I'm backing up, right? And that's mostly the case. You're backing up circuits, and so you need to know everything that's on that circuit. Here I've listed out their average use and their peak use. That could be at the peak of their cycle or the inrush current. You want to know the potential draw that these devices have, particularly if you are not using an embedded ATS type ESS, where you don't have a quick transfer time and these loads could have to all restart. You want to know what the startup amperage or power, if you multiply it by the voltage, is. So in this calculation, it's telling me that Monday through Friday, over here on the right, is the day, is it the type of day where I use the most energy, 11.5 kilowatt hours for these circuits. If I'm going to get a battery for this, I have to factor in that my PV system at a minimum is going to contribute 5 kilowatt hours. So I don't have to get as big an ESS because of that contribution. But I also am not going to discharge the ESS 100% most likely. So I want to factor that in. And then the math is done, and I'm going to need an 8 kilowatt hour battery. If I think that I have great transfer time because I have an embedded ESS to an essential loads panel, embedded ATS inside my ESS, then I have quick transfer time. I don't need to be able to back up all 5.2 kilowatt hours. I can just get something that's maybe 2 kilowatt hours of power. Now, this is obviously a small system, but it's just an example. However, if I think I have a longer transfer time, then I want to get an ESS that can handle 5.2 kilowatts at least of backup power. Okay, so just a quick word here. While you can get a battery inverter, please consider PV systems. I know there's some installers who will not do an ESS without PV. You just are saving on the size of the ESS. And for some areas, you're getting this energy from the PV system that's more valuable because it's got a clean energy credit to it. But remember, even though your PV system might be glorious in the summer on a sunny day and 30 kilowatt hours, in the winter, December 22nd, it might on a cloudy day only produce 5 kilowatt hours, and that might be the day you lose power. So you want to say that your contribution by your PV system to the ESS is based on that worst day scenario. All right, down to the calculations. And again, you're going to see this imagery later, so we don't have to go into detail here. But you want to calculate the minimum capacity you need for the battery side, the minimum power of the PV system, and the minimum power of the ESS, right? You've got to have a certain amount of power at that based on whether you're backing up everything from a cold start or just switching over and loads don't drop off because you have a quick transfer time. Understand that there are small little calculations that like the DC-AC inversion factors, some small ones. The point here is that when you get a result like 13.75, just round it up to 14. Just be clean about it. And you'll save yourself some hassles about trying to be perfect. And on that note, there are a lot of variables. It's hard to be perfect. But if you can do a modular ESS system, then you can install something that isn't oversized. And if the customer needs something more, you can add another battery module without requiring rewiring, right? Or maybe you buy two small stacks, so they have batteries in parallel, and each of those stacks can get another module if it's necessary. But you don't take the risk of oversizing and, quote, overcharging your customer. So this is a win-win for you and the customer if you have a modular approach. So in summary, we can do retrofits and new installs, and we do partial and whole home. Make sure that you have an auto transformer either embedded or you buy the external ones because you're going to want to power 120 volt circuits. And also know that auto transformer can handle imbalanced 120 volt loads, right? If you have two 120 volt bus bars in that essential loads panel, do they have to be within 30% of each other in terms of usage? Some don't require that. GoodWe doesn't require that balancing. Do you have an ESS for a essential loads panel that has an embedded ATS for fast transfer time? If it's under 10 milliseconds, then that's UPS level speed, and your load should stay alive, and that results in you not having to worry about restart times. If you are doing whole house, you obviously need some form of disconnect from the grid, both safely and timely. Can you expand the system by stacking batteries? Is the ESS solution able to stack batteries? How many can you do in a series or parallel? And make sure you know whether it's in series or parallel. Can you parallel inverters? Some inverters can't be paralleled directly. You need an external box to allow that to happen. Otherwise, they compete with each other because they're both trying to do AC waveform creation. Do you need load management? So there are plenty of solutions out there if the customer isn't self-managing. Finally, the ESS capacity is based really on doing proper load calculations. So look back at the slides to see how you can do that. And on the power side, be very careful about those inrush current loads, whether you're doing metering or just looking at the nameplate. You want to consider those because the last thing you need is for that first experience of the grid going out and systems restarting and there's too much inrush current and you don't get any backup power. So that concludes my presentation here. I just want to remind everybody that we'd love to see you at RE+, the former SPI in Anaheim in a few weeks, where you can see all our solutions, both just PV straight or with storage, and peek at what's coming up with our commercial solutions. So the rest, you'll just have to see in person. And for that, I'll hand it now over to Maria. And we can go into the Q&A part.
Yeah, thank you, Jock, and thank you, Michael, for sharing your presentation and expertise with us. In case you're coming in late to this webinar, these were Jock Patterson and Michael Mendick of GoodWe USA, who have just discussed residential best use cases and best practices for sizing. And now it's the Q&A time, as Jock just said. So I will be putting your questions to Michael and Jock, and we have a lot of interest coming in. And thank you for submitting the questions already. So this one refers to slide 39. Maybe, Jock, you can return to it. It's just like, it says, are microinverters capable of ramping down by certain amounts, or do they just shut off with the frequency change sent out?
So, of course, I would always say that depends on the microinverter, but today's microinverters should act like PV inverters and have a frequency watt response built into them. That said, anybody installing a backup system should always check that exists, that existing PV inverter, whether it's a microinverter or not, truly has the functionality of a frequency watt. Good question.
Okay, and you talked a lot about ATS. A person asks, is this equivalent to the gateway on a Tesla Powerwall?
So an external box like a gateway is an external ATS. It's just a switching device. It may have other features in it like auto transformer or metering, etc. But the main feature here is that it safely switches the loads over. And that can be something that's done inside the inverter, which means you don't need to get an extra box. Or in the case of the Powerwall, it's an external box, so you have to get an additional box to do that switching.
And how quickly can embedded ATS switch compare to an externally installed one? So how do they compare?
So just from the my thought for like GoodWe, we're under 10 milliseconds. We're about 8 milliseconds, and I think anything lower than that is just not necessary. Devices are going to shut down if you can switch over in 3 or 4 milliseconds versus 8. It really doesn't matter. I think the 10 is the key mark of whether or not you're at UPS level switching. That doesn't mean you're a UPS. That just means you are UPS-like in terms of switching. The external ones, if they use a relay, it might take a half a second, up to a half a second, 300 milliseconds to 500 milliseconds to make that switch, in which time you could lose some loads.
Yeah, exactly. Okay, Michael, is there a recommended tool to be used in the sizing of home storage?
I think we provide just training to installers, some science, just slides like that, or it depends on the battery. We combine the inverters, so it really depends on the situation. But we usually talk to every installer and give them some training. We call it quick start training about how to size PV and how to size also batteries.
And I will add, Maria, that some of the most popular platforms out there provide this for you, like Energy Toolbase, for example. And I'm not Aurora Solar, probably too. So you don't have to look for a dedicated software tool for this. You can look at a tool you're already using for proposals to help you with battery sizing.
Okay, so the IRA requires 3 kilowatt battery size for the tax credit. Is this only for separate battery purchases? And the person asks, can I go smaller if it's a complete PV system with inverter and smaller, for example, 2 kilowatt batteries?
I think that's really a question that has to be discussed locally. I know that it's a 3 kilowatt hour limit. That means, in my interpretation, we haven't talked too much because this legislation is pretty new. So we haven't too much experience, to be honest, with installers about that and how they get tax credits back. But I would say, everything that is bigger than 3 kilowatt hours falls into the category. And maybe even if you add more batteries later on, you still will be eligible. that's again, it's a brand new legislation. We have to
Indeed, yeah.
get more experience with that.
Yes, yes. Mhm. All right. Okay, Jock, when using the hybrid inverter, the ESG2, can we limit the charging current of the battery only when the battery is being charged from the grid?
So my understanding is that you're just able to set the times when you're charging. If you want to set it so it charges only from the grid, that's a great question, because normally people are wanting to charge only from the PV side, right? They're not supposed to be charging from the grid, or it's more expensive to charge from the grid. So we know you can set the time. I'm not sure you can set the charging rate, and I'll have to get back to someone on that. That's a good question. That's not a question I normally get. People are interested in how fast you can charge it, not if you could slow it down.
Sure. Okay. And Michael, is there any impact on battery system selection when the consumer has either a one-phase versus a three-phase electricity grid connection?
I think there is. We are usually now used to the one phase, single phase, split phase, but we have other solutions as well which we can help with.
Right. So this one, um, yeah, well, there are a couple of more general ones. Can you give more insights on BESS integration and communication and interaction with heat pumps and EVs with V2H and V2G ability?
Well, for GoodWe, we're going to be, if you come to the show, you'll see our EV charger solution with your inverter. But I think the nature of the question here is using EV battery storage as a additional storage option. And that bidirectional nature isn't something I'm covering in this presentation at this level. So it's an important question, but it's in a more advanced one. So I'm dealing with what people are coming across more today, more in the bell-shaped curve of typical things people are coming across. And that it's a great question, but it's a little bit early to be mainstream.
Indeed. Okay. And what is the recommended depth of discharge for GoodWe batteries?
So we can work with several different batteries. So that may vary. But for example, on that BYD HVL that we saw, we will discharge that to 90% typically. It doesn't mean you can't change it, but that's recommended to leave a little bit in the tank for dark start purposes or other needs. And then we have our own battery that I believe has even greater depth of discharge. I just don't know the number off of it. And that battery will be displayed at SPI, so we can talk about it then.
Yeah, that would be interesting to see. And what are the capacity degradation rates of current GoodWe batteries in percentage loss over the number of load cycles? And is this linear or does it accelerate over time?
This is similar to the last question in the sense that the GoodWe battery is coming this fall. So you can see it at SPI, but the batteries that we currently work with, for example, again, the BYD, they'll have a guarantee after 10 years or so of having, I'm somewhat making these numbers up, 80%, 78% of their original power after 10 years of use. But they actually think it'll be higher than that. So just for warranty purposes, they say 78 or 80, but they think it's more like 85, possibly higher. I assume we're similar, but I would like to be able to say exactly what we're going to be. I just don't have that information yet.
Yeah, sure thing. So, Michael, instead of setting the time for the battery to charge from the grid, can we also set the level so that the battery gets charged from the grid only when critical?
When it critically needs it, I think is what we're saying. When it gets to a certain low level, I do believe there's that. I haven't set up. This is a great question, but it often gets asked to the after sales team, the people after you buy it. And so I'm on the pre-sale side, and I haven't gotten that question yet. But I think it's a legitimate question, and I believe you can. I just don't know how you do it. Yeah, but it makes sense that you would want to do that.
So for how to, I mean, we talked about some of this, but how to properly estimate air conditioning consumption of for BESS capacity.
So I think you're looking at the tonnage or BTUs of the AC unit. You want to keep in mind the lock rotator amperage. So the initial startup, what that requirement is. So you get an ESS that has the right power. And then you have to remember the AC, if it's not a variable type drive for the AC, it's going to cycle on and off, right? It's going to go in its idle phase and then its operating phase. And so you're going to be getting an up and down pattern in your usage. And you have to have an understanding of what percentage of the time does it stay in the upper. And then you can calculate the average use rate, right? And again, those meters that you can attach tell you all that. You don't have to sit there and watch what's going on. Those meters, you can put a clamp around, a CT around the wire, so you don't have to open up the actual circuit. You can see what's going on and gauge it that way, and not just count on the nameplate rating, because some of these older AC units do not do the same thing they did when they were first installed. Like they often will have a higher startup amperage. And by the way, it doesn't mean you have to get a bigger battery, a more powerful battery, right? It's hard to find a powerful battery out there for inrush currents. So take those loads and put a hard starter kit on them or a soft starting device. And you can greatly reduce the inrush current requirements for those devices and not have to buy 8 battery stacks to get your AC started.
Absolutely. So maybe just one last one to wrap things up. So a more general one, what are the advantages and disadvantages of AC versus DC coupled battery systems for residential use?
So they're both advantageous for their intended purposes, right? I wouldn't do DC coupling to an existing PV system unless you know that your DC coupling solution can be backfed by an existing PV system and has a frequency watt functionality. I would just do a PV hybrid inverter for a new install, and for a retrofit, I would get just a battery inverter. Now, if someone really wants to add more PV to an existing PV system plus storage, then you could get a PV hybrid inverter to add more PV plus the built-in battery inversion electronics all in one unit. So just be careful that the existing PV system is able to backfeed into that new PV hybrid inverter without any problems. In other words, the PV hybrid inverter is bidirectional on the backup circuit.
Yeah, that great. Thanks, Jock. And with that, we are running out of time. I think that's a great place to leave this for today. First, a big thanks to all of you for joining us from across the globe, and a big thanks to all of you who submitted a question. We really do appreciate those contributions to the discussion. A special thank you, of course, to Jock and Michael, and to all at GoodWe for initiating this session today. And of course, to my colleagues at PV Magazine behind the scenes who have worked to pull things together yet again. So this webinar is coming to an end, but we have much more for you to enjoy. The September edition of PV Magazine will be out next week. We have just wrapped up the whole thing and sent it off to the printers, and you have a first look at the amazing cover we got from illustrator Ariel Ilone. This month, we are looking into the trend of localized manufacturing for both solar and batteries, and the factories mushrooming all over the world with a focus on the US, India, and the EU. Also, developments in Brazil, Turkey, and Indonesia, and more are very well covered in the magazine. And we have a journalist looking into the impacts Ukraine energy has suffered since the invasion by Russia earlier this year, and the beginnings of a regeneration plan that is very much led by renewables. So all of that and a whole lot more, 96 pages in total we have on the latest in solar and energy storage coming your way next week. So head over to pmagazine.com and pick up a subscription today. Of course, make sure to use the webinars 10 subscription discount code that you can see there on your screens. And on top of that, we always have fresh solar industry news published online or on our websites. Yeah, with the most read stories now, including new battery system, always hot news, and an interesting story about 100% renewables powered world. So we also have quite a few webinars coming up. So already next week, Shaping the Future of PV Manufacturing, hosted by my brilliant colleague Mark Hutchins. And then on Thursday, you'll see me again talking about utility scale projects and string inverters. And for more information, of course, head to pvmagazine.com/webinars. That's just about it. And one last thing, a survey will pop up after the webinar. We'd appreciate your thoughts and feedback on how it all went. We do this for you, not for us, so any insights will go far. Thank you all for watching this webinar, and for wherever you are in the world, I wish you a good day or good evening, and we look forward to seeing you again soon. Bye now.